A telescope designed to find other Earths found things that make no sense at all. The Kepler Space Telescope spent years staring at a single patch of the cosmos, and its mission was beautifully simple: to watch for the tiny, regular dips in starlight caused by planets passing in front of their suns. It was a search for the familiar, for worlds like our own, but what Kepler delivered was a catalogue of cosmic weirdness that left astronomers utterly baffled. By the end of this journey, you will have explored 20 of the strangest, most mind-bending puzzles ever recorded by a machine. We are talking about stars that dim in impossible ways, planets that orbit in mere hours and should have been vaporized long ago, and signals so bizarre they sparked serious talk of alien megastructures. This is not a story of what we expected to find, but of what we never imagined could exist. So what does it say about our universe that its rulebook seems to have so many missing pages? The very first strange signal from Kepler was so extreme it shattered all expectations. A star designated KIC 8462852, later nicknamed Tabby's star, began behaving in a way that defied every known rule of astronomy. Planets, even giant ones, cause their star to dim by maybe 1 or 2% when they pass by. But this star's light was dropping by a staggering 22% at times, in chaotic, jagged dips that had no regular pattern. It was as if something colossal and utterly misshapen was drifting in front of it, blocking out massive chunks of its light for days or even weeks on end. This was not a clean, repeating eclipse. This looked like a swarm of something, or one single, impossibly fragmented object. The initial, most natural explanation was a huge cloud of comets shattered by the star's gravity. But the numbers never quite added up. The amount of dust and debris required was almost unimaginably vast. That is when a few scientists dared to voice the idea that had been lurking in the back of everyone's mind. Could this be evidence of alien engineering, a so-called Dyson swarm, a vast collection of energy-collecting structures built by an advanced civilization? The alien megastructure hypothesis was never the leading theory, but it captured the public imagination because it highlighted just how bizarre the data truly was. Here was a signal so strange that intelligent design had to be considered, not as a belief, but as a legitimate point of contrast against the natural explanations that were struggling to fit. Years of follow-up observations have tempered that initial shock, pointing more toward uneven clouds of interstellar dust as the likely culprit, yet the fundamental mystery remains. Why is this one star shrouded in such an extraordinary opaque veil? Tabby's star taught us a crucial lesson: that our first encounter with the truly unknown would look nothing like a neat, clean planet. It would look messy, inexplicable, and profoundly unsettling. If Tabby's star was a puzzle of shadows, the next discovery was a puzzle of fire and gravity. Meet Kepler 78b, a world that by all rights should not be here at all. This planet is almost exactly the size of Earth, and its density suggests it is made of rock and iron, just like our own home. But that is where the similarities end, because Kepler 78b completes an entire orbit around its star in just 8.5 hours. To put that into perspective, a year on this world is shorter than a single workday on Earth. It orbits so close to its sun that its surface is a global ocean of molten rock, with temperatures soaring beyond 2,000 degrees Celsius. The gravitational tides are unimaginable, stretching and squeezing the planet constantly. The central mystery is brutally simple. How did an Earth-sized ball of rock get so close to a star without being utterly obliterated? One leading theory paints a picture of cosmic violence. Astronomers suspect Kepler 78b might be the ghastly remnant of a much larger planet, perhaps a gas giant like Jupiter that wandered too close to its star. In this scenario, the star's ferocious heat and gravity would have stripped away the entire massive atmosphere, leaving behind only the naked, rocky core we see today, a planetary corpse orbiting its executioner. Another idea suggests it formed further out and migrated inward, but that journey should have ended with the planet being torn apart or swallowed whole. Its very existence defies our models of how solar systems calm down and settle into stable arrangements. This scorched, screaming world is a testament to the chaotic and destructive forces that can shape planetary systems, proving that some planets are not born in their current hell, they are survivors of a cataclysm. Yet while some worlds scream of chaos, others whisper of impossible harmony. Among the thousands of planetary systems Kepler discovered, one stands out for its breathtaking order. The star known as Kepler 11 is home to not one or two, but 6 confirmed planets, all orbiting closer to their sun than Venus does to ours. The truly astonishing part is how they move. These 6 worlds orbit in an almost perfectly flat plane, like marbles rolling on a single, vast tabletop. In our own solar system, the planets orbit in roughly the same plane, but with noticeable tilts and wobbles, a legacy of gravitational bumps and cosmic traffic accidents over billions of years. Kepler 11's flawless alignment is different. It is a precision that defies probability. This kind of flat, coplanar architecture suggests a history of profound tranquility. Astronomers believe it means these planets formed from a calm, spinning disk of gas and dust around a young star and have lived their entire lives undisturbed. No passing stars have yanked them out of alignment. No catastrophic collisions have sent them careening onto wild new paths. Their peaceful coexistence in such a tight space is a puzzle in itself, as their gravitational influences should have destabilized their delicate dance long ago. This system is a cosmic fossil, a pristine snapshot of a planetary family that formed together and stayed together, untouched by the violence that seems to shape so much of the cosmos. It challenges the idea that chaos is the default, proving that under the right, serene conditions, solar systems can achieve an almost architectural perfection. So we are left with a beautiful contradiction, a universe that creates molten hellscapes orbiting in mere hours, right alongside serene families of worlds moving in flawless, silent harmony. What other forms of cosmic order are waiting to be found? But the universe's capacity for wonder extends beyond single suns. Kepler's data revealed a world that seemed plucked from science fiction, a planet orbiting not 1 but 2 stars. This is Kepler 16b, the first confirmed real-world Tatooine. Imagine standing on its surface, looking up to see 2 suns tracing complex arcs across the sky, casting ever-changing double shadows. Kepler spotted this world by observing the subtle, repeating dimming of light as it passed in front of both stars in its system. The detection was a technical marvel, requiring the telescope to untangle the planet's tiny signal from the complicated, overlapping brightness patterns of the binary stars themselves. These stars are locked in a tight gravitational dance, circling each other every 41 days, while the planet orbits them both at a much greater distance. The gravitational environment is a delicate balancing act, a cosmic waltz where the planet must navigate the combined and shifting pulls of 2 gravitational masters. For any potential life, this dance creates profound challenges. The planet's orbit is stable, but its climate would be anything but simple. With 2 energy sources, the amount of light and heat reaching the surface would vary significantly depending on whether the stars were side by side, eclipsing each other, or at opposite points in their dance. This could lead to extreme seasonal shifts far more dramatic than anything on Earth, with temperatures swinging wildly over relatively short periods. The very concept of a stable, temperate zone becomes a fluid and complicated calculation. Yet, the mere existence of Kepler 16b proved a monumental point. It showed that planets can form and persist in the chaotic cradle of a double star system, dramatically expanding the potential real estate for worlds in our galaxy. If a planet can survive here in this gravitational whirlpool, then perhaps the Star Wars vision of galactic civilization was not so far-fetched after all. The discovery forces us to ask what other seemingly impossible environments might actually cradle hidden worlds. The serene order of a double sunset is one thing, but Kepler also witnessed a world in its final, agonizing death throes. The data for the candidate planet KIC 1255754 reveals something startling, not a clean, repeating dip in starlight, but a lopsided, smeared-out shadow. Each time this object passes in front of its star, the dimming is uneven, with a strange, drawn-out tail on the trailing edge. The explanation is as dramatic as it is brutal. This is not a solid planet transiting, it is a planet disintegrating. Imagine a rocky world orbiting so close to its ferociously hot star that its surface temperature exceeds 1,500 degrees Celsius. At that infernal heat, rock does not just melt, it sublimates, turning directly from solid into a vaporized cloud of dust and molten droplets. The star's radiation and stellar wind then blow this material off into space, creating a vast comet-like tail of debris that trails behind the dying planet. Every orbit, this cloud of destruction passes in front of the star, blocking a variable amount of light and creating that bizarre, messy signal. Calculations suggest this world is losing mass at a staggering rate, perhaps millions of tons of material every second. At that pace, the entire planet could be completely evaporated within 100 million years, a geological blink of an eye. This is not a slow geological process, it is a violent, real-time unraveling. We are not looking at a stable world, but at a ghost, a cloud of what a planet once was, still held in a gravitational embrace as it slowly vanishes. What does it feel like to watch a world die? Kepler gave us a light curve, a graph on a screen, that translates into a spectacle of cosmic destruction on a scale we can barely fathom. If some planets are survivors of past violence, this one is a prisoner of a present and inescapable doom. While some planets face total annihilation, others endure a different kind of chaos, a relentless celestial wobble that twists the very concept of a year. Kepler 413b is a gas giant locked in a gravitational argument with its host stars, a dance that has left it permanently off-kilter. This planet orbits a pair of stars, but unlike the stable Tatooine world, its path is anything but flat and steady. The entire orbital plane of Kepler 413b is slowly rotating or precessing, like a wobbly spinning top laid on its side. Imagine drawing a flat circle around a center point, then slowly twisting that entire circle like a hula hoop. That is precession. For this world, the twist is dramatic, completing a full wobble every 11 years. This constant, slow-motion tumble has a profound consequence. It completely redefines seasons. On Earth, our seasons are caused by the tilt of our axis as we orbit the Sun. Here, the seasons are dictated by the wild, changing tilt of the orbit itself relative to the binary stars. Over that 11-year cycle, the planet's path will sometimes take it directly between its two suns, bathing it in intense, constant light, a scorching double summer. At other points in the wobble, its orbit will orient it so that for part of its year, it passes behind one star as seen from the other, plunging it into a profound and lengthy darkness, a deep cosmic winter. The shift between these extremes is not gentle or predictable in the way we understand. A summer might last for several of its short, 66-day orbits, only to give way over the next decade to winters of equal severity. The climate on this gas giant itself would be a storm-racked nightmare of shifting energy, but the true thought experiment lies with any potential moons. A large, Earth-like moon orbiting this unstable giant would experience climate chaos on an epic scale. Its primary source of light and heat would be the binary stars, but its view of them would be constantly altered by the wobbling path of its host planet. You could have decades of relatively stable, warm conditions, only for the moon's orbit to gradually precess into a century-long era of deep freezes, all while being tugged by the gravity of a restless gas giant. It is a scenario where long-term climate stability, the very foundation for complex life as we know it, becomes almost impossible. Kepler 413b shows us that a planet can have a permanent address in a solar system without having a stable home, its skies governed by a clock that resets the rules every 11 years. The universe is not done defying our expectations for what a planet should be. From worlds of molten rock and disintegrating dust, we turn to planets that seem to be made of nothing at all. Welcome to the bizarre realm of the super puffs. These are worlds like Kepler 51b and Kepler 51d, gas giants roughly the size of Jupiter, but with a critical and mind-bending difference. If you could place one of these planets on a cosmic scale, you would find it weighs almost nothing. Their density is lower than cotton candy, so low that if you could find an ocean large enough, they would float. This is not a metaphor, it is a physical reality that breaks every model of planetary formation we have. A planet that size should have a strong gravitational pull, compacting its material into a dense core surrounded by thick layers of gas. These worlds, however, appear to be almost all atmosphere, vast, bloated envelopes of hydrogen and helium with no substantial solid center to speak of. How does something so massive remain so diffuse? It is as if the universe decided to inflate a planet with helium and then forgot to stop. Astronomers are scrambling for answers. One leading idea is that these are young, warm planets still glowing with the heat of their formation, and that internal thermal energy is puffing them up like a hot air balloon, preventing their atmospheres from cooling and condensing into a more compact form. Another, more exotic theory suggests we are not seeing the planet's true surface at all, but instead looking at a colossal system of planetary rings or a permanent, planet-encircling shroud of dust and ice particles, a veil so thick it mimics the signal of a puffy atmosphere. Both ideas come with serious problems. If they are young and hot, why are they not radiating more heat that we can detect? And if they are shrouded in rings, those rings would have to be staggeringly vast and stable on a scale we have never seen, even around Saturn. The super puffs force us to confront a fundamental gap in our knowledge. We thought we understood the basic blueprint for gas giants, but these worlds are built from a different set of instructions entirely. They represent a pathway of planetary evolution we never predicted, where giant worlds can remain eternally fluffy, defying gravity's relentless pull to compact and solidify. What other forms, what other textures of planet are floating out there in the dark, waiting to rewrite our textbooks once more? But the cosmos can pulse with rhythms far more delicate than the violent unraveling of a world. Among the steady blinking of transiting planets, Kepler detected a signal of breathtaking precision and beauty, a stellar heartbeat. In certain close binary star systems, like the one catalogued as KOI 54, the data reveals not a simple dip but a sharp, periodic spike in brightness. This spike occurs precisely when the two stars swing closest to each other in their elongated orbits. At this moment of closest approach, their immense gravitational pulls stretch each other, distorting their spherical shapes into ovals. This tidal distortion causes their surfaces to bulge, changing their apparent brightness from our vantage point in a rapid, predictable flash. The resulting light curve is not a flat line with a U-shaped dip. It is a series of sharp, repeating peaks that look exactly like the blips on a hospital heart monitor. Each pulse is a direct measurement of the star's gravitational conversation, a clean, rhythmic signal amidst the noise of the cosmos. This heartbeat tells astronomers more than just orbital timing. By analyzing the exact shape and timing of these pulses, scientists can peer into the internal structure of the stars themselves. The way a star distorts under tidal force reveals its internal density, how much mass is concentrated in its core versus its outer layers, much like squeezing a fruit can tell you if it is ripe or dense. These systems are natural laboratories for studying tidal forces on a stellar scale, forces that can drive internal heating, alter spin rates, and over cosmic time. even circularize wild orbits into calm, circular paths. The heartbeat star is a reminder that the universe communicates in many languages. Beyond the silent drift of shadows and the explosive fury of dying worlds, there exists this subtle, rhythmic pulse, a cosmic vital sign broadcasting the hidden physics of giant suns locked in an eternal, graceful dance. The rhythmic heartbeat of distant stars speaks of gravitational harmony, but some planetary dances are set to a far more ominous timer. Deep within Kepler's data lies a system that serves as a ghostly preview of our own solar system's ultimate fate. The star Kepler 56 has swollen into a red giant, a vast, bloated sphere of cooler gas that has expanded to many times its original size. And yet, orbiting perilously close to this stellar behemoth are two planets, Kepler 56b and c. Their existence is a profound cosmic paradox. When a star like our Sun reaches the end of its life, it exhausts the hydrogen fuel in its core and begins to burn helium. This process unleashes enormous energy, causing the star's outer layers to inflate like a hot air balloon, engulfing any worlds that orbit too close. According to all our models, these two planets should have been swallowed whole billions of years ago, consumed by the very star that gave them birth. They are like moths that have flown into a flame yet somehow continue to circle untouched. So how do they survive? Astronomers are probing two unsettling possibilities. The first is planetary migration. Perhaps these worlds formed much farther out in a safer, colder region of the protoplanetary disk. Over eons, gravitational interactions with other planets or the disk itself could have slowly nudged them inward, delivering them to the doorstep of doom only after the star had finished its most violent phase of expansion. It is a morbidly precise timing, a celestial ballet where the dancers arrive just as the stage stops collapsing. The second, even stranger idea involves the star itself. What if Kepler 56 expanded in an unusual way, puffing out more quickly or in a lopsided manner, leaving temporary pockets of space where a planet could, against all odds, slip through the expanding wall of fire? This would be a stellar evolution story with a unique and violent plot twist. Observing this system is like watching a tape of Earth's future played on fast forward. In about 5 billion years, our own sun will bloat into a red giant, its surface likely reaching near or even past Earth's orbit. The inner planets Mercury and Venus will be vaporized. The fate of Earth itself hangs in the balance, a question of whether the expanding sun will fully consume it or merely scorch it to a cinder. Kepler 56b and c show us that planets can, in some freak scenarios, persist in the infernal glow of a giant star. But they also show us the brutal reality that a star's death fundamentally reshapes and usually destroys the family of worlds it nurtured. These doomed planets circling their expanded sun are cosmic sentinels, showing us the fiery end that awaits most solar systems and forcing us to ask, when our own star begins to die, will there be any place left to hide? While the death of a star marks one end of a cosmic cycle, Kepler also peered into the violent, dusty beginnings of another. Among the youngest stars it watched, astronomers found a pattern of shadows that defied the clean transit of a planet. They called them the dippers. These are not the steady, predictable dimmings of an orbiting world, but erratic, complex fading events, as if someone were repeatedly dragging a dusty hand across the face of a flashlight. The stars showing this behavior, often found in young stellar nurseries like the Upper Scorpius region, are cosmic infants just a few million years old. They are still swaddled in the thick, primordial clouds of gas and dust from which they were born, the very material that will one day coalesce into planets. The dipper phenomenon is our front row seat to that chaotic construction process. The leading explanation is that we are witnessing colossal, irregular clouds of dust and debris orbiting within the star's planet-forming disk. These are not the fine, even sheets of material we often picture. Instead, they are likely monstrous clumps and tendrils, perhaps vast streams of rubble created by the gravitational stirring of infant protoplanets, or even the aftermath of catastrophic collisions between these embryonic worlds. Imagine two Mars-sized bodies slamming together in the darkness of a young solar system. The impact would not create a neat new planet instantly, but would vaporize rock and scatter countless trillions of tons of debris into a sprawling, opaque cloud. This cloud, caught in orbit around the star, would then pass in front of it from our viewpoint, blotting out its light in a strange, asymmetrical pattern. Kepler's data shows these dimming events can be deep, dropping the star's brightness by up to 40%, and their shapes are jagged and unpredictable. Some last for days, others for weeks, and they never repeat with the clockwork precision of a mature planet. This is the messy reality of planetary birth. It is not a gentle accretion of dust, but an era of colossal violence, of smashing planetesimals and gravitational turmoil. The Dipper stars offer a fleeting snapshot of this brief, turbulent phase. Within a few 100 million years, the dust will either clump into planets or be blown away by the stellar wind, and the star's light will clear. The shadows will vanish, leaving behind a calm, mature system with no visible trace of the chaotic construction site it once was. In these erratic flickers, we see the hidden, violent childhood of every solar system, a reminder that the serene orbits we find elsewhere were forged in fire and collision. The violent birth of planets in dusty nurseries seems a world away from the final, scorched orbits Kepler would later discover. Some worlds do not just form close to their star, they live their entire existence in a state of perpetual, screaming velocity. Astronomers call them ultra-short period planets, and they are among the most extreme environments ever catalogued. Take Kepler 10b, a world of solid rock slightly larger than Earth. Its year is not measured in days or months, but in a mere 20 hours. This planet completes an entire orbit, a full lap around its star, in less time than it takes for one rotation of our own planet. To visualize that speed, imagine a cosmic racetrack where Earth plods along in the outer lanes, taking a leisurely 365 days to complete one circuit. Meanwhile, Kepler 10b is a blur on the innermost track, screaming past the finish line over 400 times in the span of a single Earth year. Its proximity to its sun is almost incomprehensible. The surface temperature is estimated to be a hellish 1,400 degrees Celsius, hot enough to melt iron and turn rock into a global lava ocean. The very existence of these ultra-short period planets is a direct challenge to our theories of planetary migration. We understand how gas giants might spiral inward through interactions with a protoplanetary disk, but for small, rocky worlds to end up so close is a tougher puzzle. One compelling and grim explanation is that we are not looking at primordial rocky planets at all, but at the ghastly remains of something much larger. These worlds could be the naked, metallic cores of former gas giants. In this scenario, a planet like Jupiter wanders too close to its star. The star's intense radiation and stellar winds then act like a cosmic blowtorch, relentlessly stripping away the entire massive gaseous envelope over billions of years. What remains is the heavy, dense core that was once buried deep within the atmosphere, a planetary skeleton now orbiting in the very furnace that killed it. This theory of stellar evaporation would explain why these worlds are so dense and why they orbit so close. They are the final, indestructible relics of a catastrophic process. Yet, even this brutal story does not answer every question. Some ultra-short period planets are found orbiting alone, with no other planets in the system to gravitationally push them into such a deadly spiral. Their journey to the inferno remains a mystery. Standing on such a world is beyond imagination. The star would dominate half the sky, a raging furnace of light and heat. The ground beneath your feet would be molten rock, and the planet itself might be tidally locked, with one hemisphere in permanent, scorching daylight and the other in a somewhat cooler, but still oven-like eternal twilight. These are not places for life or even complex geology. They are monuments to the destructive power of stars and the strange, enduring remnants they can leave behind. If the Dipper stars show us the chaotic construction yard of planets, the ultra-short period worlds show us the final, burning scrap heap. Yet for every world trapped in a blazing orbit, there may be another cast out into the eternal cold, a wanderer with no sun at all. Kepler's data contains hints of the most solitary objects imaginable, planets utterly alone in the dark. These are the orphan planet candidates, worlds that appear to be drifting through interstellar space, bound to no star. Kepler did not see them directly, for a dark planet gives off no light to dim. Instead, it detected them through a clever trick of gravity called microlensing. When one of these massive, lonely objects drifts precisely between Kepler and a distant background star, its gravity acts like a lens, bending and focusing the faraway star's light for a brief moment. From our viewpoint, that background star temporarily brightens in a specific telltale pattern. It is a single, symmetric spike of light in the data, a ghostly signature of an invisible mass passing silently through the foreground. These microlensing events are incredibly rare and fleeting, requiring perfect alignment across unimaginable distances. But a handful of such signals in Kepler's day to point to objects with masses likely ranging from a large moon to a giant planet, all moving through the void without a stellar parent. The question of their origin is profoundly unsettling. Were these worlds born in solar systems like our own, only to be violently exiled? In the chaotic gravitational wrestling match of a young planetary system, a close encounter between giant planets can easily fling a smaller world out into interstellar space at tremendous speed, a cosmic ejection with no hope of return. It is a fate that might have nearly befallen Earth in our own system's early days. Alternatively, could some of these objects have formed alone? In the coldest, densest cores of interstellar gas clouds, small knots of material might collapse under their own gravity directly into planet-sized bodies, never igniting into a star and never acquiring an orbit. They would be dark, rogue planets from birth, never knowing the warmth of a sun. Visualize such a place, a world of frozen rock or perhaps a deep, global ice sheet over a subsurface ocean kept liquid by internal heat. Its sky would be a permanent, star-studded blackness with no sunrise, no day, no concept of a year. The only light might come from the occasional brilliant flash of a distant supernova or the slow, majestic glide of the Milky Way's band across the heavens. These orphaned worlds force us to expand our definition of a planet. Must a planet orbit a star, or is it simply a large, rounded object that formed like a planet? Their existence suggests the galaxy may be teeming with such dark nomads, far outnumbering the stars themselves, a hidden population of lonely giants and frozen outcasts drifting forever between the lights. The dark nomads drifting between stars represent one extreme of cosmic isolation, but another, more intimate form of planetary destruction may leave its signature in the very light a star emits. The star known as Kepler 170 holds a grim secret in its spectrum, a chemical fingerprint that tells a story of celestial cannibalism. When astronomers analyzed the light from this sun-like star, they found something deeply unusual, an overabundance of heavy, rocky elements like iron, silicon, and magnesium. In a star of its age and type, these metals should have mostly sunk into the core long ago, pulled down by gravity. Their pronounced presence in the outer atmosphere, the part we can see, is a glaring anomaly. It is as if you found chunks of brick and concrete floating on the surface of a lake, long after the construction site on the shore had been cleared away. The most compelling explanation is as dramatic as it is final. Kepler 170 likely devoured its own children. The theory goes that one or more terrestrial planets, rocky worlds similar to Mercury, Venus, or Earth, met a catastrophic end. Through gravitational interactions, their orbits destabilized over billions of years, sending them on a slow, decaying spiral inward. As a planet approaches so close to its star, tidal forces become overwhelming. The star's gravity pulls more strongly on the near side of the planet than the far side, stretching it. This tidal stretching creates internal friction, heating the world and sapping its orbital energy, causing it to spiral even closer in a vicious feedback loop. Eventually, the planet crosses the Roche limit, the point where the star's tidal forces exceed the planet's own gravity. At that moment, the world is torn apart. It does not plunge in whole, but is shredded into a vast ring of debris, a swirling river of molten and vaporized rock that rains down onto the star's surface over thousands of years. This planetary material, rich in those heavy rocky elements, then becomes mixed into the star's outer layers, permanently altering its chemical signature. We are not seeing the act of consumption itself, but the lingering evidence of the feast, the stellar equivalent of finding dust from a crumbled statue on the floor of a museum. This provides a chillingly direct look at planetary system dynamics. We often think of solar systems as stable, clockwork arrangements, but Kepler 170's atmosphere is a monument to instability. It shows that the calm orbits we see today are not guaranteed forever, that gravitational nudges can, over cosmic time, send a world spiraling to its doom. For any hypothetical life on such a doomed planet, the end would be a slow-motion apocalypse. The star would grow ever larger in the sky, tides would become global earthquakes, and the atmosphere would boil away long before the final, fiery disintegration. This data forces us to ask a sobering question about our own solar system. Could gravitational chaos ever send Mercury or even Earth on such a death spiral? While our system appears stable for now, Kepler 170 is a stark reminder that for some planets, the warmth of their sun is not a gift of life, but the prelude to a fiery oblivion. The serene order of a solar system is a fragile thing, shattered by the evidence of Kepler 108. This star hosts two confirmed planets, both gas giants larger than Saturn, but they move through space in a way that defies every expectation of a calm, flat family. Their orbits are not aligned in the same plane, like records spinning on a turntable. Instead, they are tilted at a staggering angle of nearly 90 degrees relative to each other. If you could stand on one of these worlds and look up, the other planet would not trace a path across your starry sky. It would appear to swing high above and then dive far below your orbital plane in a dizzying, three-dimensional loop. This is not a gentle tilt, it is a cosmic collision of orbital paths. Such extreme misalignment does not happen in a peaceful system. Planets form from a flat, spinning disk of material, inheriting its orderly motion. For two worlds in the same system to end up in perpendicular orbits, something catastrophic must have intervened long after the disk of gas and dust vanished. Astronomers see this as the gravitational scar of a violent past. The most likely culprit is a close encounter with an intruder. Billions of years ago, another star, or perhaps a rogue, Neptune-sized planet, may have passed perilously close to the Kepler 108 system. Its gravitational pull would have been like a cosmic hand swiping through a mobile, violently yanking and tilting the orbits of the existing planets. The intruder would have sailed off into the galaxy, leaving behind only this profound orbital chaos as its calling card. Another possibility is a slower, internal gravitational war, where a third, now ejected planet stirred up the system over eons before being flung out entirely. The result is the same, a solar system that looks like a poorly assembled clock, its gears turning at right angles to each other. This inclination mystery forces us to reconsider the history of our own neighborhood. We take our solar system's flat alignment for granted, but Kepler 108 proves that such order is not guaranteed. It is a prize won through a peaceful childhood, a history free of bullies passing through the cosmic playground. For any moons that might orbit these skewed giants, the sky would be a source of constant wonder and terror, with a second giant world performing impossible acrobatics overhead. a permanent monument to the day a stranger passed by and kicked over the entire celestial table. Death is not always the end, even for a solar system. The star catalogued as KIC 05807616 tells a story of cosmic resurrection so strange it defies belief. This star is no ordinary sun. It is a hot-B subdwarf, the exposed, blazing core of a star that has already died. Billions of years ago, it was a star much like our own. It exhausted its hydrogen fuel, swelled into a monstrous red giant that likely engulfed its inner planets, then shed its outer layers entirely, leaving behind only this incredibly hot, dense, and tiny core, now shining with a fierce blue-white light. Around this stellar corpse, Kepler found the impossible two-planet candidates, KOI 55.01 and .02, orbiting closer than Mercury is to our Sun. Their existence is a profound paradox. Any planets that close should have been vaporized during the star's violent red giant phase, swallowed and atomized. So what are they? Astronomers have proposed a theory that sounds like science fiction. These might be zombie planets born from the ashes of their own destruction. The violent death throes of the red giant would have torn apart not only the inner planets, but also giant planets further out. The debris from this cataclysm, a swirling mix of vaporized rock and metal, could have been caught in a disk around the remaining stellar core. From that disk of destruction, in a second act of creation, new planets could have coalesced. These would not be primordial worlds, but second-generation orphans, forged from the remains of their annihilated siblings. They are planets made from the bones of planets. The conditions on these reborn worlds are beyond extreme. Orbiting so close to the intensely hot subdwarf, their surfaces are likely scorched to temperatures exceeding 8,000 degrees Celsius, hotter than the surface of our own Sun. They might be little more than exposed cores of vaporized rock and metal, or perhaps vast globes of molten diamond formed under insane pressure and heat. Their very existence rewrites the timeline of planetary life. We thought a star's death was the final chapter for its family, but here we see it could be a brutal prologue to a new, stranger beginning. It forces us to wonder how many other stellar graveyards might hide such ghostly, resurrected worlds, silently orbiting the embers of their dead suns. The resurrection of planets from stellar ashes is a story of cosmic rebirth, but some planetary systems tell a different tale, one of hidden giants pulling strings from the darkness. The star known as Kepler 88 hosts a planetary puzzle solved not by seeing a world, but by hearing its silent gravitational echo. Astronomers confirmed two planets transiting this star, a small inner world and a larger middle planet, Kepler 88c. As they watched the clockwork rhythm of Planet C's transits, something strange emerged. The planet was not arriving on time. Sometimes it would appear in front of its star a full half-day early, other times it would be half a day late. This was no instrument error, it was a systematic wobble in the very heartbeat of the system. The cause was a gravitational conversation, a silent tug of war happening in the void. The timing variations, called transit timing variations, are a brilliant indirect detection method. Think of it like this: you are watching a friend on a swing, pushing them at a steady, predictable rhythm. Suddenly, you notice their arc is coming back to you a little faster, then a little slower, even though your pushes haven't changed. You would rightly suspect an unseen second friend is also pushing from the opposite side, their hidden force altering the timing of the swing you can see. In the Kepler 88 system, the transiting planet C is that visible swing. The gravitational pull of an unseen, massive outer world, designated Kepler 88d, is the hidden hand. Every time Planet D and Planet C come close in their orbits, their immense gravity yanks on each other. This constant gravitational nudge speeds up or slows down Planet C's journey along its orbit, making its transits arrive early or late from our vantage point. By meticulously mapping these timing deviations, astronomers could reverse engineer the properties of the hidden puppeteer. They calculated that Kepler 88d is a true giant, a planet with a mass nearly 3 times that of Jupiter. Yet, because its orbital plane is tilted relative to the 2 inner planets we see transiting, it never passes in front of the star from our point of view. It is a shadow planet forever hidden in the glare of its sun, yet its presence is broadcast loud and clear through the gravitational dance it imposes on its siblings. This discovery revealed a solar system architecture far more complex and massive than a simple glance at the transit data would suggest. It is a system dominated by a hidden colossus, a gravitational anchor that likely shaped the entire arrangement of the inner worlds. The method itself is a testament to the ingenuity of modern astronomy, proving we can find and characterize worlds we may never directly see, simply by listening to the subtle rhythms they disturb in the night. Among the many theories proposed for Tabby's star's bizarre dimming, one stands out for its sheer cosmic audacity. What if the shadow is not cast by dust or comets, but by something we cannot see at all? This is the dark matter hypothesis, a speculative but captivating idea that connects one of astronomy's greatest observational puzzles to its greatest theoretical mystery. We know dark matter exists because we can see its gravitational handiwork, the way it bends light and holds galaxies together with invisible strength. Yet for all its influence, we have never directly detected a single particle of it. It simply does not interact with light, making it utterly transparent. So how could it block a star's light? The proposal hinges on a radical possibility that dark matter might not be entirely uniform. Perhaps it can clump into macroscopic objects, chunks or diffuse clouds large enough that their sheer mass warps the fabric of space-time itself. According to Einstein's theory of general relativity, any massive object acts as a gravitational lens, bending and focusing light from objects behind it. If a sizable knot of dark matter, a so-called macro, drifted between Kepler and Tabby's star, its gravity could distort the starlight in a way that mimics a dimming event. The light would be bent away from our line of sight, making the star appear to fade without any physical material ever blocking the photons. The appeal of this idea is its neatness. It could explain the irregular, deep, and achingly strange dimming patterns without requiring impossible amounts of ordinary dust. A dark matter cloud would be invisible, could have any shape, and would not emit the infrared glow that a dust cloud should. For a brief moment, it seemed like an elegant solution to an inelegant problem. Yet most scientists view this idea with deep skepticism, and for good reason. We have no confirmed evidence that dark matter forms such isolated, dense clumps on the scale needed to lens a star. Our best models suggest dark matter is pervasive and smooth on small scales, like a fine mist throughout a galaxy, not chunky. Furthermore, to cause the observed dimming, this hypothetical macro would need an incredibly precise alignment, not just with the star, but with our line of sight from over 1,000 light-years away. The odds of such a perfect cosmic alignment are astronomically low, making it a last-resort explanation. The mainstream consensus has steadily solidified around a more mundane culprit, interstellar dust. Detailed follow-up observations, particularly with the Kepler Space Telescope, showed the dimming was more pronounced at blue wavelengths than red. This is a classic fingerprint of dust, where smaller particles scatter blue light more effectively, just like our own sky. A vast, uneven cloud of cold dust orbiting the star in a peculiar ring or swarm fits the data far better than any exotic gravitational lens. So while the dark matter idea remains a thrilling footnote, a testament to how deeply this star puzzled us, it ultimately highlights a more profound truth. When faced with the utterly unknown, our minds race to the most exotic possibilities. We leap to invisible matter and alien engineering before we consider a messy, complicated cloud of space dirt. Tabby's star's legacy may not be a discovery of dark matter or extraterrestrials, but a lesson in cosmic humility. reminding us that sometimes the universe's strangest signals have surprisingly ordinary, if complex, origins. Even the most solid-looking evidence for a new world can sometimes be nothing more than a stellar fever dream. The candidate planet known as KOI 1843.03 presented astronomers with a classic detection puzzle. Its signal was a tantalizing, repeating dip in starlight, suggesting a rocky world even smaller than Earth orbiting its sun in a blistering 4.5 hours. But a closer look at the data revealed a troubling inconsistency. The light curve was not perfectly clean and symmetrical like a solid planet's shadow should be. Instead, it had subtle irregularities, a slight wobble in the depth and shape of the dip from one orbit to the next. This opened the door to a radical alternative explanation. What if there was no planet at all? The pulsating planet hypothesis suggested this signal might be a cruel cosmic mimic, caused not by an orbiting world but by the star's own violent heartbeat. Certain types of stars are known to pulse rhythmically, their surfaces rising and falling as internal forces drive expansions and contractions. If a star had a large, dark spot on its surface, like a colossal sunspot, that spot would rotate into and out of our view with the star's spin. As it rotated into sight, it would cause a dip in brightness. If the star itself were also pulsating, changing in size and brightness at the same time, the combined effect could create a complex, periodic dimming pattern that, to our distant instruments, looks eerily similar to a planetary transit. Another possibility involved stellar flares or massive eruptions, ejecting clouds of material that briefly occult the star's surface in a semi-regular way. Distinguishing between these stellar tantrums and a genuine planet is one of the hardest technical challenges in exoplanet science. It requires examining the light curve with forensic precision. A true planetary transit is typically a symmetric, U-shaped dip. The star dims smoothly as the planet's edge first touches the stellar disk, holds steady at minimum light while the full planet is in front, then brightens symmetrically as the planet exits. The depth of the dip is consistent every single time, dictated by the planet's fixed size. Now compare that to a stellar flare's signature. A flare is an explosion, so its light curve is a sharp, asymmetric spike, not a dip. It brightens rapidly as magnetic energy is released, then fades more slowly. A pulsation or rotating spot, however, is trickier. Its dip might be V-shaped or irregular, and crucially, its depth and timing can vary because the star's surface features evolve, growing, shrinking, or moving. For KOI 1843.03, the debate hinged on those tiny inconsistencies. Could a solid body really orbit so close without being torn apart? Or were we seeing the turbulent surface of a star, its own natural rhythms masquerading as an alien world? In the end, further analysis leaned toward the planetary interpretation, but the case remains a powerful object lesson. It reveals the delicate line between discovery and illusion, reminding us that every new world found is first a ghost in the data. A signal we must prove is not just the star itself crying out in the dark. This inherent uncertainty forces a profound question. How many other candidate planets in Kepler's vast catalogue are actually stellar imposters, and how many real worlds have we dismissed as mere noise? The search for cosmic order takes its most elegant form in the silent music of orbital resonance. Far from the chaotic wreckage of colliding worlds, some planetary families move with the precision of a finely tuned clockwork. Systems like Kepler 80 and Kepler 223 are not just collections of planets, they are gravitational symphonies. Here, the orbits of multiple worlds are locked together in perfect integer ratios, a phenomenon that creates profound stability through a repeating cycle of gentle gravitational nudges. In Kepler 80, for example, 4 of its planets are linked in a chain. For every 3 orbits the innermost planet completes, the next one out finishes too. That next planet, in turn, completes 3 orbits for every 2 of its outer neighbor, and so on down the line. It is a cosmic rhythm section where each world's year is a simple fraction of the others, like notes in a chord. This is not a coincidence. Such resonant chains are thought to be the fossilized record of a very specific and gentle planetary migration that occurred billions of years ago, when these worlds were still young and embedded in the protoplanetary disk of gas and dust around their infant star. As the planets formed, they interacted with this disk, and the friction caused them to slowly spiral inward toward their star. Crucially, if they migrated at just the right, synchronized pace, they could fall into these stable gravitational locks where their orbital periods became mathematically related. Once the disk of gas eventually dissipated, the planets were left frozen in this harmonious arrangement, their delicate dance preserved for eons. The beauty of this configuration is its self-correcting nature. If one planet falls a tiny bit ahead in its orbit, the periodic gravitational pull from its resonant partner will give it a slight tug, slowing it down just enough to bring it back into rhythm at their next alignment. It is a celestial feedback loop that maintains order. This makes resonant chains incredibly stable over astronomical timescales, protecting the planets from the gravitational chaos that might otherwise fling them into collisions or eject them into the void. Yet, this perfection is also a profound puzzle. Our own solar system has hints of resonance, like the 3-2 lock between Neptune and Pluto, but nothing as extensive or pristine as these Kepler chains. Why are they so rare? The migration process that creates them requires a smooth, gradual, and undisturbed journey through the disk, a peaceful childhood that many systems may not have experienced. A passing star, a violent impact, or the gravitational bullying of a giant planet can easily break these fragile chains, leaving behind the more common, randomly spaced planetary systems we usually see. So when we find a resonant chain, we are looking at a cosmic unicorn, a system that has lived a charmed and quiet life. Its synchronized orbits are more than just orbital mechanics. They are a lullaby from the dawn of a solar system, a rhythm that has been ticking flawlessly since before the Earth was born. What does it say about our universe that it can compose such perfect, silent music in the dark? Yet even the most perfect orbital resonance cannot answer the ultimate question Kepler was built to address. Among its thousands of discoveries, one world stands as both a triumph and a profound lesson in cosmic ambiguity. Kepler 452b orbits a star strikingly similar to our own Sun, a G2-type star, and it sits squarely within its star's habitable zone, that temperate band where liquid water could pool on a rocky surface. It is an Earth-sized planet with a year 385 days long, a place so familiar in its statistics it was immediately heralded as Earth's older, bigger cousin. This should be the storybook ending, the discovery of a true analog to our own pale blue dot. But the data holds a frustrating and telling secret. Kepler told us the planet's size and orbit, but it could not tell us what it is. The fundamental nature of Kepler 452b remains a ghost in the machine. Is it a rocky super-Earth, a world with continents and oceans under a life-nurturing sky? Or is it a mini-Neptune, a world with a small, solid core smothered under a deep, crushing atmosphere of hydrogen and helium, a gaseous shroud that would create surface pressures capable of turning carbon into diamonds? The difference is the difference between a garden and a pressure cooker, and with Kepler's data alone, we simply cannot know. This uncertainty defines the current frontier. Finding a world in the Goldilocks zone is only the first tantalizing step. The true search for Earth 2.0 requires peering into its air, analyzing the chemical fingerprint of its atmosphere for signs of water vapor, methane, oxygen, the potential biosignatures that could hint at processes we associate with life. Kepler was a census taker, magnificently cataloging what is out there, but it was not equipped to be a portrait artist. That task falls to the next generation of observatories, like the James Webb Space Telescope, which can dissect the faint starlight filtering through a distant world's atmosphere and tell us its composition. So Kepler 452b, this most promising of finds, ends our list not with a definitive answer, but with the most important question of all. It is a placeholder for hope, a reminder that the most Earth-like world we have found might be utterly alien beneath its clouds. Its very ambiguity is the perfect capstone to Kepler's legacy of strange data, proving that every answer uncovers a deeper layer of mystery, and that the final chapter in the search for other Earths has not yet been written. So the Kepler Space Telescope gave us far more than a simple catalogue of other Earths. It handed us a gallery of cosmic anomalies, a testament to a universe far stranger and more creative than we ever dared to dream. From disintegrating worlds trailing their own ashes to puffy planets lighter than cotton candy, from the silent harmony of resonant chains to the gravitational scars of ancient stellar bullies, each piece of strange data is a vital clue. These are not mere curiosities, they are the jagged edges of our understanding, the places where our models crack and our imaginations must rush in to fill the gaps. Every bizarre light curve, every impossible orbit is a direct challenge, pushing the entire field of astrophysics to ask better questions and build newer, more flexible theories. The mission's true legacy is this: it revealed that for every rule we think governs planets and stars, the cosmos has an exception waiting in the dark. And this is just the beginning. The next great chapter is already being written by observatories like the James Webb Space Telescope, which will stare into the atmospheres of these enigmatic worlds, searching for the chemical signatures that could tell us what they are truly made of and perhaps what might live there. The universe has shown us its strangeness. Now it is our turn to make sense of it, to keep following these mysteries as they unfold. Subscribe and join us for more deep dives into the greatest enigmas of space.